Okay, so last week, Wednesday, we discussed the natural response of RC circuits. That is, if you have a bunch of resistors, one capacitor in the circuit, and you have a source that is energizing the capacitor. Once you remove the source, then how a capacitor is going to dissipate its energy through the resistors that are in the circuit. That's called the natural response of the circuit. And we saw that the capacitor dissipates its energy through an exponential function. Important thing about calculating the natural response or source-free response is that you must have the value of the initial value, well, you must have the initial value of the capacitor voltage. And then once you remove the source, after the change is happening, we usually take the time where the change is happening as our reference time, which is 0. So once the change happens, that initial value of the capacitor voltage does not change instantaneously. And you can easily write down the exponential function of the capacitor voltage as the initial value V0, we call it, exponent of -t over tau, where tau is the time constant. Now, who remember what is the definition of the time constant? It's the length of time where the initial value of the capacitor voltage drops down to 36% of its peak value. Right? It was 36.6% or something like that, if I remember correctly. So e to the power -1. So don't say when somebody asks you what is the definition of time constant, don't say RC or L over R. That's not the definition. That's the formula of the time constant. Definition is what Yunus said right now. So it's the length of time that in which the response of the capacitor voltage drops down to 36.6% of its peak response, which is the initial value of the capacitor voltage. Okay, so today we are going to look at the forced response of RC circuits. Forced or complete response of RC circuits. All right. What do I mean by forced or complete response? Basically, you can still have your voltage source or current source even after the change is happening and the capacitor is in the circuit. So let's say your change is happening again at a reference time. We call this at t is equal to 0. And you're flipping a switch or you're turning off and on a source, whatever the change is happening at that time. So before the change, your circuit is running. Maybe it's running for a long time. Maybe it's running for a short time. We will see. And after the change, something is changed in the circuit. You are introducing more resistors. You are changing the value of the source. You're bringing a new source, whatever is happening. But the whole idea is circuit is not becoming a source-free circuit in general after the changes happen. So now your source is going to be there before the change and after the change. Maybe you are adding another source, or maybe you are just removing one source and keeping one source in the circuit. Under those conditions, we calculate the forced or complete response of RC circuits. And in general, the forced or complete response of RC circuits, the voltage across the capacitor, let's say, VCT, is comprised of two components: the forced components or steady state component, and the natural response. So this is whether it's a capacitor voltage, whether it's a current, all those quantities, they are comprised of two components. A steady state. What is the steady state? A steady state means what is the final value of the capacitor voltage or capacitor current or inductor voltage or inductor current. That is, final value means when you let the circuit go on for a very long time and you fully charge the capacitor, you fully charge the inductor if you have inductor in the circuit. So what will be that voltage value? That's the steady state response of the capacitor voltage. Yes. Yeah, so capacitor will start acting as an open circuit, inductor will start acting as a short circuit. We're going to discuss inductor, of course, later on. So that's the steady state voltage value across any component, not just capacitor, across any component, that the value at which the circuit has reached to its steady state. And a steady state means when all the transients are gone. Transients mean when you are having change in the circuit, voltage change or current change. Those are called transients. But when all the transients are gone and your circuit is operating at a constant DC value, the constant DC current, constant DC voltages, and so on and so forth. That state is called the steady state in the circuit. So capacitor voltage, since we are going to find the capacitor voltage first, capacitor voltage is going to be the steady state value and is going to be the natural response like we did the last time. So in general, the capacitor voltage and capacitor current is the same thing, a steady state value and the natural response. Capacitor voltage is given by, as I said, V steady state, and the natural response from last week, what we were discussing, can be given by an unknown A. It's not the initial value, but A e to the power negative t over tau. So A is an unknown constant. We don't know that value. We will find that value from the circuit. This is the same natural response. It's an exponential response with the time constant tau. And remember that time constant tau, anytime you're trying to figure that tau, you are going to figure that out from the natural circuit. That is, you're going to remove all the sources from the circuit, combine the resistors, and then one resistor in parallel with one capacitor, and then calculate what is the tau, that is R equivalent times C. So it always comes from the natural circuit, that tau. So you're gonna open circuit the current sources, short circuit the voltage sources, and then calculate R equivalent times C. And that will be the time constant tau. So very simple process to find the forced or complete response of a circuit. And again, I'm not going into the derivation of that. There's a lengthy derivation. And then from that, we figure out that you have two components, a steady state and the natural. But instead of going into derivation, just understand that you will have two components. The complete response is going to be comprised of two components, and you will have to find both components in order to give the complete response of different voltages and current. And we are looking for the capacitor voltage initially, but we can find any voltage or any current in the circuit. So let's go ahead and start working on problems. So let's assume now that you have let's say this is R1, R2, R3, and R capacitor. say this is VS1 10 volt and VS2 5. These are the values, let's assume. This totally random circuit I'm drawing. And this is going to be, let me make the change as well. Let's, this is going to be U minus T and U. The all right, let's write down the capacitor voltage expression for time t or greater or equal to 0. All right, as far as those two sources are concerned, who can tell me how VS1 is going to behave? I'm going to ask you. All right, so Chris, how VS1 is going to behave? Okay. Natasha, how VS1 is going to behave?
If value is less than 0, it
You're talking about time values. No, I'm asking you, you're talking about time values, right? Okay, no, that's incorrect. Anyone else? VS1. Yeah. So VS1, what you said, it's opposite. And Natasha, VS1 is going to be on as long as time is not 0. That is for all the negative values of time. Your reference time is we are taking at 0. And then it's going to turn off for all the positive values of t, 0 and all the positive values of t, because the argument is going to become negative for all the positive values, right? So it's going to be on and then it's going to turn off at t is equal to 0. What about VS2? Jose, how VS2 is going to behave? Okay, the rest? Very good. So for all the negative values of t, it's going to be off, and for all the positive values of t, it's going to be on, and starting at t is equal to 0. So they're going to be switched around at t is equal to 0. One is going to turn on, and the other is going to turn off. Yes. 5ut. Yeah, u is the unit step function. Yeah. Unit step function is basically turning on and off that source based upon its argument. If the argument is negative, then that source, that unit step function is going to be 0. If the argument is positive, that unit step function is going to be 1. So whatever is the multiple of that unit step function, that's going to turn on and off that value, 5 or 0 for VS2 and 10 and 0 for VS1. So both are DC sources. So change is happening at t is equal to 0. That's our reference time. So the first thing that we need to do, of course, since we are trying to figure out what is VCT for t greater or equal to 0, the first thing that we do is we find out what is the value, what is the initial value on the capacitor voltage for before the change is happening. So t less than or equal to 0, Vc is equal to what? And that we will call our initial capacitor voltage V0. Okay, so for that, we can draw the circuit real quick. So this is going to be on, then we will have R1, then we will have R2, we will have the capacitor. All right, since V2 is going to be off, how I should treat V2? It's going to be short out. It's going to be shorted out. All right, once I short that out, that means my R3 and R4 will be in parallel with the short. That means they're just going to be gone. There's no current that will flow through R3 and R4. Everything is going to go through the short, if there is any current going through that. And I can easily remove R3 and R4. Okay, so who is going to tell me now what will be the voltage across the capacitor? Okay. What should we calculate to calculate the voltage across the capacitor? So that voltage is going to be across what? No, that's not R1. That voltage is across R2, yeah. So you said that's correct thing. The voltage across R2 basically is the same voltage as the voltage across capacitor. And remember, capacitor is acting as an open circuit. It's running for a long time, t less than or equal to 0. When this source is on, it is fully charged. So it's acting as an open circuit. So whatever is the voltage across R2, assuming capacitor is open circuit, that voltage is going to be the voltage across the capacitor. So how are we going to find that voltage out? Who's going to tell me? Voltage division, very good, easy. Voltage division. Using voltage division, we see 0 negative, which is equal to V0, is equal to VR2 will be equal to Vs R2 over R1 plus. Okay, let me write down all these values in my MATLAB. R1 is 10, R2 is 33, R3 is 44, and R4 is 57. Vs1 is 10 and Vs2 is 5 and capacitor is 100 microfarad. Okay. Now my V0 is Vs1. This is Vs1. Vs1 times R2 divided by, and that is 7.67. So that's my initial voltage across the capacitor. And now I'm going to analyze the circuit after the change. After the change, my VS1 is going to become 0. That means I will short that source out. My VS2 is going to become active, and rest of the components are going to be there. So if I want to draw my equivalent circuit after the change, I have R1 and R2 in parallel, C, VS2, and then R3 and R4. So this will be my equivalent circuit when the change is going to happen. And as you can see, it's called what we call forced circuit. It's a forced circuit because you have a source in the circuit. Capacitor does have energy stored in it, but the source is also there. So the capacitor charges are going to rearrange because after the change, circuit is changing. So the capacitor energy is going to rearrange. It's going to go from one level to the other level. Whatever level is that going to be, we have to figure that out as in terms of capacitor voltage, as how the voltage is going to change across the capacitor. Now, one thing is interesting, as you can see, VS2 direction is positive, negative, as you can see. That means the final value on the capacitor voltage, we are expecting to be positive on the right side and negative on the left side. So the polarity on the capacitor voltage, the final value is going to be opposite of the initial value. Initially, we have 7.67 volt as the polarity that is shown on the circuit. We're going to keep that polarity because we have to find VCT according to that polarity. Yeah. So those are the final values, right? So between it assumes the final value, it is going to go in the transient state. It's going to go from one state to the other state, and that's the transient part in the full response. So that's this part, natural response, in which it is changing from one value to the other value, and then this is the final value of the capacitor voltage, right? So now we can write down our generic equation. Sense? Plus A e to the power. We can do two things. We can stick with, let's do this. We can change the polarity because that might be easier for us. And then towards the end, we can again show the opposite one is true for the other polarity. So we can go with positive here and negative here for the time being. The first thing that we are going to find out is what will be the steady state response or steady state value of the capacitor voltage. When time is going to hit infinity, that is, capacitor is going to be fully charged again. All right, guys. So what do you suggest? Let me put down one thing. Let me just write it down here so you don't get confused when we write down the equation. Okay, steady state value. How are we going to find that steady state value? Who is going to tell me? Again, assume that capacitor is fully charged. Steady state means when the circuit is running for a long time, capacitor is fully charged. What you're expecting across the capacitor in that case? Okay. Capacitor is going to be open, yeah. And when capacitor becomes open, then what will be the voltage across the capacitor? So between those two nodes where the capacitor is connected, means what is the voltage across? At those two nodes, you subtract the voltage, and that's the voltage across the capacitor. So what's the voltage at the junction of R3 and VS2? Voltage here and voltage here. What is the voltage at VA or A, node A? VS2. What will be the voltage at node B? And that is going to be VR2 minus VS2. But what is VR2? That's what I'm asking. Well, we are trying to figure out VC. Yeah. If you remove capacitor, capacitor is fully charged. It's open circuit. If you remove capacitor, assume you're not removing physically, but you remove capacitor. How much current is flowing in R2 in that case? Zero, exactly. He said it already. There's no current in that part on the left side because the source is on the right side of the circuit. So there is no current in the left part of the circuit. If you remove capacitor, if you assume it's an open circuit, that means no current is flowing from the source through the capacitor to the other part of the circuit. That's zero. So the voltage across the capacitor will be simply Vs2 in this polarity. Remember, we changed the polarity. So I'm taking this polarity right now. So that is going to be equal to Vs2, right? And Vs2 was 5 volt. So once again, guys, this is the analysis. That's not difficult. You're not doing any math or anything, but you're looking at the circuit and analyzing it. That's important. That is important because if you make mistake over here, basically all of your program is incorrect. So that's my steady state value. So I can write the equation down. VCT is equal to VSS, which is 5 volt. So 5 plus A e to the power negative t over tau. Okay, now what is tau? Now we know the formula, R times C, right? But what will be tau? Hold on. Let other people also answer. And remember, you have to make the circuit natural circuit when you are calculating tau. That is, you have to remove all the sources when you're calculating tau. So look at the circuit, remove the source, and then tell me what will be tau. Again, R1 plus R2, R1 and R2, you think they're in series? Yes, Rodley, you wanna take a chance and tell me what will be the equation for tau in that circuit? Time constant. Again, remember, remove the source when you're calculating the equation for tau. Remove the source means if it's a current source, it's going to be open. Voltage source will be short, of course. Yeah. Yes, Rudy, go ahead. Okay, let's just start. All right, Natasha, let's start from there. Natasha, what do you think? They are in parallel. All right, Chris. And no, I understand, but R1, R2 parallel, and what else? Okay, so in parallel with C, yeah, that's true. And why are we not considering R3 and R4? Explain that as well. Very good, excellent. Because VS2, remember, you're removing VS2. That means you're shorting VS2 out. So that short circuit will be in parallel with series combination of R3 and R4. That means R3 and R4 in parallel with short circuit is just going to become a short circuit. So R3 and R4 will be gone from the circuit because they are in parallel with the short circuit. So it's going to be R1 and R2 in parallel to each other, and that will be multiplied by the capacitor, and that is your time constant. R1 parallel to R2, that's the equivalent resistance times the time constants. Once again, remember, you have to remove VS2, you have to short it out. That means R3 and R4 in parallel to a short circuit is just going to become, this whole thing is just going to become short circuit, basically. Any resistance that you put in parallel to short circuit, you take the equivalent of that, it's going to be the short circuit. Okay, so the tau value is going to be, go to my parallel. The tau value is Rp, R1, R2 times C. So I have 767.4 microsecond. 767.4 microsecond. So that's the value of tau. Okay, the equation is not complete because we do not know what the value of A is. Remember, value of A is not the initial value of the capacitor voltage. A, we have to figure that out from the initial value, but it's not the initial value under many situations. It may or may not be initial value, but in general, it's just an unknown constant right now. So how do we find that unknown constant A? We find that using the initial value. That is, we evaluate this equation at t is equal to 0 positive. That is just after the change is happening. At t is equal to 0 positive, Vc 0 positive. All right, what will be the value of Vc 0 positive? Same as just before the change happened, because capacitor value cannot change instantaneously. So that value we calculated at 7.67. That's the initial value. And that's why we calculated that, so that we can figure out the value of the unknown constant. So once, yes, go ahead. That's true. I forgot. Thank you. That's going to be negative 7.67 because we changed the polarity. So before our polarity was opposite, and now that. So that's why I put a negative sign. And put an arrow over here just so that you guys don't forget about that. Okay, so then I have negative 7.67 in this equation. Negative 7.67 is equal to 5 plus a. E to the power 0 is going to be 1. When you put t is equal to 0, is 1. So a is going to be negative 5 minus negative 7, negative 12. Negative 12.67. That would be my, I'm sorry. Yes, you're right. This is 5 and this is 1. This is 5 final value and then this is 12. 12.67. Very good. So that's our capacitor voltage. It's changing its direction. This is the final polarity. 5 volt is the final value. And then it is changing from negative 7.67 to 5 volt. And the difference between the two, of course, is 12.67. So it is going to go something like that. When you plot it, or when you simulate it, this is what you're going to see. You have negative 7.67 before t is equal to 0. And then at t is equal to basically 0 positive and stuff is negative 7.67. And the final value is going to be negative 5, positive 5. Let's say positive 5 is here. And then in between, it is going to change. How it is going to change? Increase and get to positive. Yes. Mhm. Did I for tau? Yeah, you showed it because it is coming from the natural circuit. Yeah, you can plot it. I don't know if I'm doing the plot correctly or not. It may go down and then go up. Let's see. So if I do the plotting, let's say I have. I'm just going to do for t. T is equal to 0, and let's say tau by 100 and 5 times tau. I think it's going to go down and then it's going to, and my equation is Vc is 5 minus 12.67 times exponent of negative tau, negative t over tau. And then I can plot t comma vc. Yeah, it's gonna go it's gonna go down first around -8, and then it's gonna surge to the value 5. So it's not gonna go straight. I can go ahead and add t less than 0 values as well, which is going to be negative. No, that is negative 7.67. Sorry, yeah. So it is going straight. Yeah. So this is negative 7.67, right here. So this plot is correct. It's going to be negative 7.67, and then it's going to rise until 5. Just to refresh your memory as how you're going to plot any function, basically you take the time value, time range, vector, equation, and then of course plot. You did that plotting in MATLAB software class many times. To increase the width of the line, because initially it's going to be thin line, but if you do line width in quotes and then choose 2, 3, 4, whatever, it's going to make it thicker basically. Yeah. So that's how the capacitor voltage is going to change from initial value to the final value. And again, if we want to keep the polarity to be the same as it was given to us, then it's going to be opposite. You're going to have 7.67, and then it's going to go down to -5 volts. So it's just going to drop down and then -5 to show that the polarity is going to be opposite in the final circuit. But since we kind of change the polarity, then according to our new polarity, this is going to be the graph. I guess any questions? So this is pretty much a standard method. Again, the method is not difficult to remember. It's the analysis that you have to be good at. That, you know, when the source is gone, it's short circuit or open circuit, how you're combining the resistors, what voltage you're calculating. Those things you should look at the circuit, and then you can analyze it in your head, and you can say, okay, this is what it should be. Because other than that, the process is not difficult. You're not even applying any, most of the time, you're not even applying any KVL or KCL or any mesh analysis or nodal analysis in these type of circuits. All right, let's go to another problem. All right, so it says IS2 Okay, let's see. All right, two things we have to figure out in this: capacitor voltage and the power dissipated in R2 at 10 milliseconds. And that switch is opening at t is equal to 0. So it's going to open up at t is equal to 0. Okay. So again, look at the circuit, analyze it, and see how the circuit is behaving. Assume again it's running for a long time before the switch, before our reference time, which is t is equal to 0. What is happening at t is equal to 0? Of course, switch is opening, and what else? Okay, so what is happening at t is equal to 0? Switch is opening, and what else is happening? All right, so that part, of course, left part is going to be cut off from the circuit, and IS2 is going to turn on because it's 20 UT. So that is turning on. That's what's happening at the reference time t is equal to 0. So again, look at the circuit, establish what's happening at the change. If you don't establish that, you don't know what to do. So at the change, at the reference time t is equal to 0, switch is going to open up, left part of the circuit is just going to be out of the circuit, and IS2 is going to get activated. So the first thing we're going to do is to find the initial voltage on the capacitor, because we need that voltage to find the equation for the capacitor voltage for t greater or equal to 0. So for t less than 0, assume circuit is running for a long time. Okay, if circuit is running for a long time, what is going on before the change happened at t is equal to 0? What your circuit is going to be? Hold on. Yes, Zoris, what circuit, what is going to be the circuit before the change is going to happen? At t is equal to 0, before that, how do you look at the circuit? Just tell me what components are going to be there. Yeah, just tell me that. In the circuit, yeah. So in the circuit, which components are going to be there before t is equal to 0? Okay. So everything will be there. Well, it's just going to be there. It's going to be open. That's a different thing. But you will still keep it in the circuit. Assume it will be open. But what other components are going to be there? I mean, we are trying to figure out the initial value on the capacitor. So of course, capacitor is going to be there, of course. Yes, Chris. I'm sorry? Everything but IS2. What I'm going to do with IS2? Okay, if I open it, what other things, what other component is going to be gone? R3. So R3 and IS2 are going to be gone, and rest of the components will be there. All right. So VC0 negative just before the change is happening, which will be equal to VC0 positive, which we call it the initial voltage across the capacitor, is going to be equal to what? What voltage is going to appear across the capacitor in the circuit? Yes, Rudley. What will be the voltage across capacitor in the circuit? How are you going to calculate that? Yeah, that's what we are calculating. Okay, to calculate what? Yeah, to calculate what? VC, to calculate what? We are calculating VC, but to calculate that, you say apply voltage divider and calculate what voltage so that we can find VC. No, don't give me the formula. Give me what voltage you're looking for using voltage divider, which voltage you're trying to figure out. Well, VC, but voltage across R2, that's what you're trying to figure out. That's VC, voltage across R2, because you're applying voltage division here. You're not applying voltage division with capacitor, of course. Capacitor is open. You're applying voltage division between R1 and R2 to figure out what is the voltage across R2. That voltage is going to be the same as VC. Okay, so V naught is Vs1 times R2 divided by R1 plus R2. 5 volt. That's my initial value of the capacitor voltage. All right, T greater or equal to 0. The first part we're going to do for capacitor voltage is going to be the capacitor steady state value plus the capacitor voltage natural response. All right, how the circuit is going to look like after T is equal to 0. If I have to redraw the circuit, how the circuit is going to look like after T is equal to 0. Yes, Natasha. How the circuit is going to look like after T is equal to 0.
That would short out the area.
You're removing R1, R2, and Vs at T is equal to 0. Okay. So what will be left in the circuit? Okay. Is that correct? Is that correct? T is equal to 0, yeah. So that's correct. I will keep IS2, R3, and C in the circuit only. Jose, is that correct? Huh? No, you tell me. Don't ask me. Tell me what will be part of the circuit still when you at time T is equal to 0, when change is happening basically at time T is equal to 0. Say it again. No, again, don't ask me. You tell me. Don't ask me what do I want to do. I'm asking you. what will be part of the circuit at t is equal to 0? Okay, so those three components that Natasha said, only those three components. There's no maybe, okay? when you're solving a circuit, there's no maybe. Either it's going to be there or it's not going to be there. Yes, Chris. Yeah, the switch is opened up, right? Switch is opened up. That whole R1 VS1 is gone. Whatever is left is after t is equal to 0. R2, C, R3, IS2. I don't think it's difficult. You see what the switch is opening, what is getting out of the circuit. This part is getting out of the circuit right here. R2 is not getting out. So R2 capacitor. R3 and source. This is your circuit for t greater or equal to 0. R2, C, R3 and source. All right. Next question, what is going to be the steady state value of the capacitor voltage? Who is going to tell me that? What does a steady state mean? What's going to happen at a steady state to the capacitor? Come on, guys. It's going to be open. Come on, guys. I mean, really, seriously. I mean, I don't know what to do. A steady state, when it's running for a very long time, steady state, capacitor is fully charged, it's going to be open circuit. So when it's going to be open, what will be the voltage across the capacitor? How are we going to find that voltage? Okay, one student is giving me all the answers, correct answers. Come on, guys, you need to. How are we going to find that voltage? Anyone else except Yunus? Yunus know how to find that voltage. How are we going to find that voltage? Yes, Natasha. Derivative of IS. IS is a constant value. Derivative is 0 for that. I mean, I don't know why you're bringing derivative here. It's a simple DC circuit. R2 plus R3 times IS is the voltage across the capacitor. No, that's not correct. All right, Jose, what will be the voltage across the capacitor, steady state voltage? If it's taking you that long, I'm going to ask someone else. Yes, Chris. No, you open the capacitor when it is fully charged. Yes. Okay, so give me that question. Yes, 2 times R2, exactly. It's not difficult. C is open circuit. C is gone. You have only one loop. The current in the loop is IS2. You're trying to figure out this voltage. That's the voltage across R2, which is IS2 times R2, Ohm's law. I don't have, guys, I don't have a good feeling about what's going on in the class, to be very honest. For the simplest of the things, if this is the struggle, then I don't know. All right, 44 volt. All right, next thing, let's write down here. Time constant. Who is going to tell me what will be the time constant in this case? All right, Gloriana, what will be the time constant? All right, answer the question. How do you calculate time constant? What do you do when you're calculating time constant in an RC circuit? In an RC circuit, when you're calculating the time constant, what is your criteria to calculate the time constant in an RC circuit? I know you know. Yes, there is. It has to be in the natural state. Excellent. Very good. So when it's going to be in the natural state, what's going to happen? Sources have to go out. So in this case, if you remove the source, what's going to happen? Okay, if you remove the source, answer the question. If you remove the source, what components will be left in the circuit? Say it again. Which resistors and capacitor? Source. What you're doing with the source? When you say source is gone, what's going to happen to the source? If it is short, then R3 will be there. It's opened, right? It's opened, R3 is gone, only R2 and C are left in the circuit, in the natural circuit. So simply time constant is R2 times C. (22 millisecond). Okay, so now we can write down the equation for VCT, which is the steady state value 44 plus A e to the power negative t over tau. We know tau is 22 millisecond. Question, how are we going to find A? Using? Say it again, Rudy, you said something? Okay. Using the initial condition. Using the initial condition. So we're going to evaluate this equation at t is equal to 0. All right, at t is equal to 0, our capacitor voltage we calculated was 5 volt. Five minus 44, negative 39. So we have capacitor equation now. VCT final voltage is 44 volt. So 44 minus 39 e to the power negative t over. at t is equal to 0, you can see the answer is going to be 5 volt for 44 minus 39, which it should be. And then as t value will increase, the final value is going to hit 44 volt. Starting from 5 volt, it's going to go all the way up to 44 volt. All right, quickly, we're going to do the second part and then we're going to take the break. Any question about this, by the way, so far? Yes, there is. If you have calculated tau value somewhere and then it's clear, then you don't really have to do that. If you put it, that's fine as well. Calculated that over there, it's written there. Okay, second part is what? Calculate the power dissipated in R2 at 10 milliseconds. So this is our final circuit. How are we going to calculate the power dissipated in R2 at 10 milliseconds? Who's going to tell me? It's very easy. Yes, Chris. Say it again. V times what? V times N? I. Oh, and what is that I? Power in R2. No. Which V you're talking about? Voltage across R2 is what? Okay. And that times IS2. Okay. All right. So we can do so, but which what will be the voltage at 10 milliseconds? How are we gonna figure that out? Okay, we have to use the formula and figure out what is the value at 10 milliseconds. So multiple ways to do that. Power dissipated in R2 at 10 millisecond. All right, so that's going to be, since voltage across R2 is the same as VC, so we're going to find VC. We can write down PR2 at 10 millisecond. We can do it a couple of ways. We can do VC at 10 millisecond square over R2. That is one way to do it. The other way to do it is VC 10 millisecond times IS2. That's because IS2 is the voltage. Oh, wait a minute. We cannot do IS2 because IS2 is going through C and R2 both. So that's not going to be correct. Because capacitor is not open circuit at 10 milliseconds, it's still discharging. So that is not possible. This is the best way to do it. Now, if the capacitor is open circuit, if it's running for a very long time, it becomes open circuit, then yes, the voltage that is, the current that is going through R2 is IS2. But if not, then that's not the current going through that. So it's simply, we can just simply use this. T is equal to 10 millisecond. And VC is 44 minus 39 times exponent T over tau. And P is VC squared divided by R. 168.4 milliwatt. 168.4 milliwatt. Yeah. I did put, I'm sorry. Yeah, T I put 10. Oh, why did I put negative? Yeah. Yeah. No, my mistake. It's a different value. Sorry. Good catch. Yeah, I don't know why, but I. Okay, let's go and calculate it again. VC first, and then the power. It's going to be different value, of course. 138.3 milliwatt. 138. 138.3 milliwatt. Yeah, I didn't see it. There was a negative sign. Oh, another mistake I made. I didn't put negative over here. So I put T over tau. It's negative T over tau. So we'll do it again. Negative T over tau and then calculate power. And that's Oh, 168 because I put negative T. So it basically balanced out the positive T that so I made two mistakes earlier. I put T negative and then here I put positive. So it balanced that out. So the power is still 168.4, which we calculated it was correct, although we put we make two mistakes, so two negatives became positive. 168.3 million. 0.4 million. All right, guys, then we're going to take a break and start in about 10 minutes. Next page. Okay. Do some calculation real quick. See, this one is 10. R1 is 10. All right. So let's go. All right. Switch is closing at 5 milliseconds. Yes. This has 1 unit step, right? No, this always on, but it depends on the switch when it's going to become part of the circuit or not. Yeah. Okay, so this is the circuit. Now once again observe the circuit and see what's going on first. So time t less than 0, what's happening in the circuit? Is any source activated time t less than 0? IS1, there's no IS1. Yes, activated time less than 0, t less than 0. All right, anyone else? Jose? Yes, Lazaro? What's going on before t less than 0? Any source activated? No, that's the right answer. No. Then ut means that's going to be activated at t is equal to 0 and all the positive values of t. So that's not activated. Switch is open because switch is going to close at 5 milliseconds, which is t greater than 0. So that Vs2 is out of the circuit. So there is no source that is going to be sending current in the circuit unless capacitor is already charged. Nothing is going to happen before 10 t less than 0 unless the capacitor has some charge stored in it. So if the initial value of, if there's no initial energy in the capacitor stored, then capacitor voltage is also 0. And there's really nothing going on before t less than 0. So, yeah.
That's natural response. Charge
Because the circuit was running before t less than 0. But that's what my question was, right? Is there anything happening before t less than 0? And the answer was, in this circuit, there's really nothing happening. No source is activated before t less than 0. Now, again, if I give you a charged capacitor and you put that capacitor, then something is going to happen. But in this case, since I did not give you any information, you're just going to assume that capacitor is discharged and there's no energy stored in the charge. Generally, that information is given to you, but if it is not, then you can assume that information. So, unless it is given to you that VC0 negative is equal to 10 volt, that means it's a charged capacitor. It has energy stored. And you have to assume that as initial condition for this type of circuit, let's say, right? But if it is not given to you, you will assume VC0 negative is going to be 0. It is discharged. So T less or equal to 0. No source is part of the circuit, and if no energy is stored in the capacitor, then the initial value of the capacitor voltage is going to be 0 for t less or equal to 0. So there are two changes happening here. What are those two changes? One change at t is equal to 0. What's happening at t is equal to 0? Vs1 is getting activated, and then next change is happening at 5 milliseconds when the switch is going to close. So Vs2 is also going to become part of your circuit. So in this type of problem, of course, you are going to evaluate the circuit between the first change and the second change, and then after the second change, right? Because there are two changes that are happening. So the first, between 0 and 5 milliseconds, that's your evaluation for the first circuit. So 0 from this analysis, you are going to figure out what is the capacitor voltage and initial value for the next stage, that is after 5 milliseconds. So for this time period, we don't have the switch closed. So this part of the circuit is gone, including R4, because of course, if the switch is open, then R4 is not going to be part of the circuit. So we will have VS1, R1, C, R2, and R3. Capacitor, R2, and R3. And let me write this down. Calculate VCT and ICT expressions for t greater than 5 milliseconds. After the second change, we're gonna write down those expressions. So this is my VS1, R1, capacitor, R2, and R3. This is going to be my circuit between 0 and 5 milliseconds because the switch is still opened. At 5 milliseconds, the switch is going to close. Okay, so the goal here is to find out what is the capacitor initial voltage so that we can write down the capacitor expression after 5 milliseconds using that voltage. So in this circuit, again, we're going to use capacitor voltage is this, VC. So capacitor voltage is going to be the steady state value of the capacitor plus the natural response of the capacitor. Now, although the circuit is going through another change at 5 milliseconds, and capacitor may not be fully charged, but when you're writing the equation, you still have to consider if the circuit is running for a very long time, how much voltage is going to appear across the capacitor. That's the steady state value of the capacitor voltage. Right? So you still have to assume that circuit is running for a very long time, and what will be the steady state value of the capacitor voltage in that case. So looking at the circuit now, who is going to tell me how we are going to figure out that steady state value of the capacitor voltage? What will be that value? Because we are just writing the expression right now, and then we're going to figure out what is the value of the capacitor voltage at 5 milliseconds, and that's going to be the initial condition for the next time phase that is greater than 5 milliseconds. So, but to find that value, you need to have the expression of the capacitor voltage. Okay. Yeah. Yeah, we still assume that this circuit, it is going up to infinity. Assume that, okay, right? When you're writing the equation, you still have to assume that. But from that equation, remember, from that equation, you can put any time and you can find the voltage, right? So you're going to put 5 milliseconds and you're going to see what is the voltage at 5 milliseconds. That's going to be the voltage for the next phase, right? So equation is important, and to write the equation is the same procedure. You assume the circuit is running for a very long time to get the steady state value for the capacitor voltage, and then the natural response of the capacitor voltage, A e to the power negative t over tau. In this case, we're going to have 2 different taus, by the way. But let's just concentrate on this. So this is your circuit. How are we going to find the steady state value of capacitor voltage? Yes, Chris. Say it again. We are looking for the capacitor voltage when it is running for a very long time. How R2 and R3 are going to be parallel? Yeah, right, but we're looking for the voltage. So R2 and R3, they are not parallel. You're saying R2 and R3 will be parallel to, huh? Yeah, R2 and R3 are in series, and that is parallel to the capacitor. Yeah. Well, when you say R2 and R3 will be parallel, it appears that R2 and R3 are in parallel to each other. So, okay. So, yeah. So, R2 and R3 are in series with each other, and that combination is parallel to capacitor. So, whatever the voltage drop across R2 and R3, that's the voltage drop across the capacitor. How are we going to find that voltage? Okay. What will be the expression? R2, R3 parallel again? Why you keep saying R2, R3 in parallel? They're not in parallel. We just discussed that. Yes, R2 and R3 in series. R1 plus R2 plus R2. All right, let's see. So steady state value, we know, I'm going to call it VC naught is equal to VS1 times R2 plus R3, R1 plus R2 plus R3. 8.4615. Okay, so that is the capacitor voltage steady state. If it keeps on running for a very long time, it's gonna hit 8.4615. And what will be the value of the first time constant tau 1? Yes, question. Getting different answer? Oh, let me check my values. Maybe my values are incorrect. VS1, let me see. VS1 is 10, R1 is 10K, R2 is 22K. Capacitor is 1 micro, R3 is 33K, R4 is 47K, R5 is 1K, VS2 5. My values are correct. Okay, all right. Okay, question. What is going to be the time constant value? We're going to call it tau 1 because again, the circuit is going to be different after 5 milliseconds, and we're going to have another time constant. But from this circuit, how are you going to figure out what is the time constant value? Who's going to tell me that? No. Yes. Time constant from this circuit. Say it again. No. Very good. Excellent. R2 plus R3 in parallel with R1 times C because voltage source is going to be short circuit. So R1 is going to become parallel to R2 and R3 and times C. Yes. Not this circuit. Next circuit is going to be another tau. For this one is tau, the first tau. So I'm calling it tau 1. Yeah. But for the next phase, circuit is going to be different. So that value of tau will be different as well. Yeah. No, I said this circuit, right? This circuit. R1 plus R2 in parallel with R1 times C. Yes, Zoris? Yeah. Yes. Sure. So where R1 is going to go if you short it? If you open it, that is if it's a current source, if you open it, then R1 is gone. But if you short it, then R1 is still connected in the circuit. Yes. No, R2 plus R3 in parallel to, sorry, yeah, that's incorrect. R2 plus R3 in parallel to R1. R2, R3, that's good. Good that, see, that's good that you catch. R2 plus R3 parallel to R1, okay. Let's calculate that. R1 is parallel between R3 plus R2, R3 plus R2, and R1 times C. 8.46 millisecond. 8.46 millisecond. All right, guys. To find the value of A, we use the initial value of the capacitor voltage. What is the initial value of the capacitor voltage? 0. Exactly. We discussed that. It was resting. It's 0. Which means this equation is going to give you 8.4615 plus A, and A will be equal to negative 8.46. So between that time, 0 to 5 millisecond, capacitor voltage equation is 8.4615, 1 minus e to the power negative t over tau 1. Since 8.4615 is common, I just took that out. If I want to draw this thing, this will be 8.4615. Eventually, if you keep it running, then it's going to hit 8.4615. But we are not keeping it running because our change is happening at 5 milliseconds. 5 milliseconds. So we are going to figure out what is the value at 5 milliseconds. That's why we wrote the equation. After 5 milliseconds, of course, the equation is going to change. So these dotted lines represent that if I want to plot this equation for all the time until infinity, then it's going to go like this, and eventually the voltage is going to become 8.4615. But it's not going to happen because 5 milliseconds the change is happening. So whatever the voltage is coming, that will become the initial voltage of the capacitor at 5 milliseconds. Right? Make sense? Vc and Vc 5 millisecond equals, let's calculate that, t is equal to 5 millisecond. What do I have? Vc naught times 1 minus exponent of negative t over tau 1. 3.7753. That will be the capacitor voltage at 5 milliseconds. Now the second phase. T greater or equal to 5 milliseconds. Because the second change is happening at 5 milliseconds when the switch is going to come and become part of the circuit. Hence, both sources are going to be part of the circuit at that time. VS1, R1, capacitor, R2, R3, and R4 and R5. R4 switch, R5 VS2. So switch is going to be closed. It's going to be short circuit. R4, R5, and VS2. That's the circuit for the second time. Pardon me, sir. Okay, VC again, we're gonna go with the same. That is VCT is equal to VC steady state plus VC natural response. Okay, guys, now in this case, now you're gonna figure out what would be the steady state value of the capacitor voltage. What should I do to find the steady state value of the capacitor voltage? Okay, so I can apply, again, the steady state means capacitor is acting as an open circuit after being fully charged. So you will assume that, you don't remove, you will assume that the capacitor is not there, it's open circuit. And you're trying to figure out what is the voltage at that node between R1 and R2. So this voltage you're trying to figure out. Okay, I have this voltage. If I know this voltage, then I can easily figure out what this voltage is going to be. So I want to know what this voltage is right here. Call this node A. If I know the voltage at node A, then of course I can easily find out what is the node, what is the voltage between R1 and R2. How? Somebody can tell me how I'm going to figure out the voltage between R1 and R2 if I know the voltage at node A. What method you're going to use? If I know the voltage at node A, which we can use single node, so nodal analysis. If we know voltage at node A, how are you going to figure out the voltage across capacitor? All right, it's one step at a time. Let's go and find voltage at node A. But this, again, you have to plan ahead, because if you don't know, you're like, okay, I'll figure out this voltage. But after that, that's not your answer, though. Your answer is the voltage here. But if you don't know how to get this voltage, you cannot proceed. But anyways, let's find voltage at node A first. Nodal analysis. And why I'm not using mesh analysis? Say it again. It's going to be two equations here. It's going to be two equations. All right, here. So I'm going to keep IR1. So IR1 is going towards, let's assume my IR3. And let's assume my IR4. All right, KCL at node A. All right, Natasha, what will be the KCL equation at node A? No, we are opening VC. You're opening capacitor. That's open. So there is right now, don't worry about that. That's open. You have R1 and R2 connected in series. No, KCL. Give me the KCL equation. KCL equation does not have V. KCL equation does not have V. Yeah.
I want
Okay, IR1. Okay.
and
Okay, and your equation is not complete. Equation means that you have two sides, right? So what is the other side? Hmm? No, not second node. There's no second node. There's node A. There's one node only. There's no second node. Yes, KCL equation. Mhm. There's no IR2. It's IR4, IR3, IR1. 3. Okay, very good. So what you're saying is correct, but the other side is 0 for you. So IR1 plus IR4 equals IR3, or IR1 plus IR4 minus IR3 is equal to 0, right? IR1 plus IR4 equals IR3. Okay, now apply Ohm's law on this to write down, to apply the nodal analysis. All right, IR1. What will be the equation for IR1 in terms of nodal analysis? So this is KCL equation. Now apply nodal analysis. Okay. Okay. VS1 minus VA over R1 plus R2. IR4. IR4. First IR4. No. Look at the direction of IR4. Very good. IR3. Very good. Don't look at the direction. Remember, look at the direction. I know you must have done all the currents are always going away from the node. No, if the current is giving you going towards the node, then you write the equation according to that direction. Don't assume that it is going away if it is shown that it is going towards. All right, so now we're going to find VA. So VA will be equal to, I'm going to take all the VS on the right side, keep all the other constants on the left side. So VS1 over R1 plus R2 is one constant, VS2 over R4 plus R5 is another constant, and that will be divided by 1 over R1 plus R2 from this VA, 1 over R4 plus R5 from this VA, and then plus 1 over R3. Okay, so let's do that. VA is equal to VS1 divided by R1 plus R2, R1 plus R2, plus VS2 divided by R4 plus R5, divided by 1 divided by R1 plus R2, plus 1 divided by R4 plus R5, and plus 1 divided by R3. Parentheses, parentheses, parentheses. I think it should be okay. 5.06 or 5.07 rather. See if you get the same result. All right, now we know VA. 5.07 volt. So now the important question, how are we going to figure out VC? Who is going to tell me? You're the only one passing the course, that's the problem. And I want everyone to pass the course. Not just pass the course with good grade. Yes, how are we going to find the voltage VC if you know everything? You know VS1, you know R1, you know R2, you know VA. Voltage at VC, yes. So if you are doing this problem and I give you that branch and I ask you calculate the voltage at that node between R1 and R2, how are you going to figure that voltage out? Hello? How are you going to do that? And if you, for voltage across R3, we know 5.07 volt. Chris, what you going to do? Okay. But VC is not the voltage drop across R2. Okay, so if voltage division is not what you're going to apply, what else you're going to do? Yes, Rudy, you were saying something? Gloriana, how are you going to do that? VS1 minus what? That's the voltage across R1 and R2. But VC is not the voltage across R1. All right, Jonas, go ahead, since we don't have time. How are you going to do that? Yes, very good. Excellent, very good, excellent. So we will find IR1 first. VS1 minus VA over R1 plus R2. That's IR1 using Ohm's law. Once we know the current passing through R1 and R2, then VS1 minus the drop in R1, which will be IR1 times R1, is going to be the voltage at that node VC. One point 154 microampere, 154.2 microampere. .45. 8.46 rather. So that's the value of the steady state voltage across the capacitor. So far we were only figuring out the steady state voltage across the capacitor, the first part. So the capacitor voltage is 8.46 plus A. Now this is important right here. Minus. So when you are, there are two ways to do this basically. One way to do this is you reassign the second time as your reference time 0. And then you write down e to the power negative t over tau 2. Tau 2 we have to figure out. So you basically shift your reference time. The first reference time was t is equal to 0 when you found the first equation. And then since the next change is happening at 5 millisecond, then you say, okay, now since I'm writing the equation with respect to 5 millisecond, let me reassign that time as my new reference time as t is equal to 0. So you shift your time scale. That's one way to do it. The second way to do it, you keep that time, t is equal to 5 millisecond, but you put down in the numerator, when you put e to the power negative t over tau, you put down e to the power negative t minus 5 millisecond over tau. So you don't shift the reference, but you kind of take that 5 millisecond, subtract it from the actual time, and then put down divided by whatever tau 2 value is. Whichever way is there is going to give you the correct result. So let me do it with the second way, because our time starts at t is equal to 0 when the circuit is started, and then change happened again at t is equal to 5 milliseconds. So I'm going to write this down as t minus 5 millisecond, 5 exponent negative 3 over tau 2. Why we are doing this? Because to find the value of A, we should put that B, because A was the coefficient that we have already assigned from the first one. So let's call this coefficient B. Because to find the coefficient B, we're going to apply the initial value of the capacitor voltage, which was at 5 millisecond. So when you put 5 millisecond, the value that we calculated from the last time period, if you just put t over tau 2, then it's going to be 5 millisecond over tau 2, and this is going to give you some result, and that is going to give you an incorrect value of B, because you want this term to become 1 basically at the initial time. This term becomes 1 at the initial time, whatever the initial time that you're putting. Now again, if you refresh your time and at 5 millisecond you assume it is 0, then you can put e to the power negative t over tau 2, and then you can take at time t is equal to 0, and then you put that value at 5 millisecond that you calculated for capacitor voltage. Assume that that's the value at the new reference time, which is time t is equal to 0. Both ways are okay. I'm just going to go with the second, in which I'm not going to reshift my time scale. I'm going to keep it at t is equal to 0, and then the next change is happening at 5 milliseconds. So I'm going to subtract that change from this time. Okay, tau 2. Now another question for you guys. What will be tau 2 from this circuit? Because the circuit is changed, so our time constant is going to be different as well. What is going to be tau 2? What will be the equation to calculate time tau 2? Yes, Chris? There are a bunch of R's, so which are? Okay. Very good. Very good. Very good. Excellent. Excellent. Very good. So VS2 and VS1, of course, natural circuit to calculate tau, they're going to be short circuited. So R4 and R5 will become in series, which will be in parallel to R3. That parallel combination will be in series with R2, and that whole combination is in parallel with R1 times C. Excellent. Let me do it here so everyone can see that. So from this circuit, there's no room to write here, so let me just do it. Tau 2. All right, what was that? I'll forget about the resistors. So R4 series with R5 parallel to R3. R4 series with R5 parallel with R3. This whole thing is in series with R2. And this whole thing is in parallel with R1. And then times C. R4 plus R5 parallel to R3 plus R2. Let me see it one more time. R4 plus R5 parallel to R3 plus R2 in parallel with R1 times C. R4 plus R5 parallel to R3 plus R2 parallel to R1 times C. Okay, let's do that. Tau 2 is parallel combination of R4 plus R5 and R3, and we're adding R2 in there plus R2, and this is again in parallel with R1. This parallel with R1. So R parallel R4, R5 parallel to R3 plus R2, not 2, plus R2, and that's parallel to R1. So that's another parallel here, RP, and that is multiplied by C. So 8.23 millisecond. Now observe how easy it is again if you have the parallel function. Only one line you have to write, and then you get the result. 8.235, so I'll say 8.24. 8.24 millisecond. Okay, so at t is equal to 5 millisecond, VC 5 millisecond was, we calculated as, what was the value? 3.7753. So we plug in that value in the equation. At 5 millisecond, 3.775 equals 8.46 plus T. Because when you put 5 millisecond again, 5 millisecond minus 5 millisecond would become 0, so exponent is going to be 1. And value of B is going to come out to be B is 3.775 minus 8.46, negative 4.685. So the capacitor voltage VCT equation is 8.46 plus minus 4.685 e to the power negative t minus 5 millisecond over out. T greater or equal to 5 millisecond. 5 millisecond. And this is our part 1. back just to make sure. Calculate VT and ICT expression from for T greater, okay. All right, so we have VT. How are we going to calculate the current expression if you have the voltage across the capacitor? Therefore, yes, anyone? IC is C dV over dt. Take the derivative of this expression, 8.46 will be 0, and then you're going to have negative 4.685 e to the power negative t minus 5 exponent negative 3 over tau 2 times negative 1 over tau 2. The current is going to be 4.685 over tau 2 times C e to the power negative. And this thing is going to be what? 4.685 times C times and divided by tau 2. 5.68 exponent negative 4, so 568 microampere, 569 microampere. 569 e to the power negative t minus 5 exponent negative 3 over tau micro. So we take the derivative of the voltage and write down the current expression. All right, since we are out of time, last question quickly, who's going to tell me? We have to find out IR1 expression. All right, so let's go to the circuit. IR1 expression, who's going to tell me what will be the expression for IR1? Yes. VS1 what? No, but capacitor is not open right now. Yeah. General expression, we're writing general expression. Okay, so R1 is not the current passing through resistor. Yeah, I'm asking for IR1, but VS over R1 is not IR1 for sure. And that we discussed like hundreds of times, that how to apply Ohm's law on a resistor. All right, anyone, quickly, since we're out of time. I know you know that. All right, Zores, IR1 expression, how are we going to do that? No, what type of equation is that? Jose. You are close, but there's one issue in there, but you're very close. All right. Yes, Gloriana. VC plus VS1 over R1? No. Zaro. Okay, no. Chris. Yes, Rasha. Give me the equation. Give me just variables. Equation in terms of variables. No. We already discussed that. No. All right. Go ahead, Yunus. Yunus. Vs1 minus Vc over R1. Why it is so hard for you guys to apply Ohm's law on R1 to get current? Vs1 minus Vc over R1. Vc is the voltage at that node between R1 and R2. That's why Jose, you were close, because again, you are not looking at the current direction, Jose. You're putting Vc minus Vs1, but the current is going from Vs1 to Vc. Vs1 minus Vc over R1. IR1 is equal to Vs1 minus Vc over R1, which will, now Vc expression, of course, we already determined the Vc expression, which is this. So you're going to plug this equation. I'm not going to do it right now. You're going to plug that equation over here and then solve it. And then this is going to be your expression for IR. Okay, since we're out of time, I don't think I'm going to write it down, but just have to plug in the expression for Vc over. Yes, Chris. Second, there will be a homework is due on Wednesday, right? So there will be quiz on Wednesday, of course. All right, so this is what we're going to do. Let me stop.